So I love wearing cute, colorful sweaters when the weather permits, but one thing about my sweaters is that some are made out of wool, which is a debatable comfort material, but that's another topic. Anyway, whenever I take the sweater off, I notice that the hairs on my arms are all stood up, which is a funny sight to see. Any idea why this happens? If not, that's exactly what we will try to understand by the end of this video. So, an important rule in physics is Coulomb's law, which gives us a value for how strongly two or more particles push or pull on each other. So first, once I write this down, I want to start off by discussing the formula for Coulomb's law and why it's formatted the way it is. So imagine you have two charged particles which happen to be opposite of each other. So we have a positive, and maybe we can do this one a sad face, a negative. And so both of the particles are attracted to each other because they're opposites, right? But this attraction also comes with a force. And so in our equation, we want to know that F is present. And that's electrostatic force, which is represented by newtons. So we know that force has the SI units of newtons. And then we also know that each particle is charged. As I mentioned, this one's positive, this one's negative. So we can label them as Q1 and Q2. And they're measured in coulombs, which is a C. But another thing that's present in the distance is the distance between the two particles. So unlike area or other concepts in academia, r is not representative of radius here. Instead, r is going to be the variable for distance, and so we'd be using this in the equation, and it's measured in units of meters. So this distance here is our r, and r is measured in meters. And then one last variable, though, that is Coulomb's constant, which is represented in units of newtons. And sometimes I look up constants when I don't remember them, I will admit. And this one comes up as 8.988 times 10 to the 9th. So our constant is 8.988 times 10 to the 9th. And then it's like newtons times meters squared per coulomb squared. But lucky for us, we could just plug this constant in as 9 times 10 to the 9th newtons. Yay! So our equation is going to look a little something like our constant times our Q1 times Q2, so the charges, over our distance squared. Perfect. So great, now that we have our equation, let's get into a problem and learn how to use it. So this problem over here is from week 1A on Wiley Plus. It's the third question on there, and we're about to solve it. So in a vacuum, two particles have charges of Q1 and Q2, where Q1 is equal to positive 4.8 microcoulombs. They are separated by a distance of 0.35 meters, and particle 1 experiences an attractive force to 4.1 newtons. What is the value of Q2 and what is its sign? All right, so I first want to draw a picture so we can imagine this scenario. And I really like the happy faces that we drew above, so I'm going to mimic that. So we have Q1 is a positive charge. Let me label this as Q1. And then we have our Q2, which we have no idea what the value of Q2 is. So it's mad and it's confused. And then we have a distance r. And the distance is 0.35 meters. But we also have a force number. So, or a value for force, I should say. So it says that particle 1 experienced an attractive force of 4.1 newtons. And since they're opposite signs, then we also have this particle experiences a force of 4.1 newtons. So our goal here is to get the value of the second charge and its sign. I probably shouldn't have said that they're opposite forces because we don't really know if that sign is negative yet. But we can find out its sign and its second charge by isolating Q using our Coulomb's law equation on one side and moving the equation around so that it looks a little differently and we can get that answer. So again, our Coulomb's law equation is force equals our constant times Q1 charge and Q2 over R squared. And since we're moving everything around, we want to multiply both sides by R squared. Now that cancels out. And then we're going to divide this by K times Q1. Now that cancels out. So ultimately we're left with Q2 equals R squared times the force over constant times the charge of Q1. So now we can plug in our values, which makes our life a little bit easier. And we see that Q2 equals our R squared. Now we go up here. R squared is 0.35 meters squared times our force, which is 4.1 newtons, over our constant, which is 9 times 10 to the 9th newtons, and then times 4.8 times 10 to the negative 6 coulombs. And that is the value of our positive charge there. So once we plug that into our calculator, we should get a value of 1.1639 times 10 to the negative 5 coulombs. And since the force is attractive, the charge must be negative because opposites attract. So our answer is actually going to be negative 1.16 times 10 to the negative 5 coulombs. And now let's see if we can answer the sweater question. So this is the solution to our problem, but remember I talked about that sweater thing before? Well, we know from Coulomb's law that the opposite charges attract, so that means that like charges repel. And when I remove my sweater, electrons are transferred and the hairs on my skin become positively charged. So then those hairs repel each other, and since they are all the same charge, they end up standing. So here, these attract, but then what's going on with my sweater is the second I take it off, then basically these little hairs all become charged positively. And remember, since they're not opposites, then they're actually gonna repel each other. It's pretty cool. So yeah, that's Coulomb's law in a nutshell, and I hope that